How can information such as sound or video be stored and transmitted as electromagnetic waves? Are magnetism and spin related? Information such as sound and video is stored and transmitted as electromagnetic waves. The process involves the interaction of electric fields and magnetic fields. Here is a brief overview of this process. 1. Digitalization of sound and video information. Sound and video information is first converted into digital data. 1. Sound information is converted from analog audio signals to digital audio, while video information is converted from analog video to digital video. 1. This digital data is represented by bits, which are binary digits, zeros and ones. 2. Encoding of digital data. Digital data is represented by a sequence of bits, and the encoded data is transformed according to the format used for communication. 2. For example, audio is compressed and encoded using codec algorithms. 3. Generation of electromagnetic waves. Digital data is transformed into electromagnetic waves. 3. In this process, an electric field is generated, and the frequency, amplitude, and phase of the electromagnetic wave represent the characteristics of the data. 4. Transmission of electromagnetic waves. The generated electromagnetic waves are transmitted through wireless or wired communication. 4. During this process, electromagnetic waves propagate through air or other media. 5. Reception and decoding of electromagnetic waves. At the receiving end, electromagnetic waves are detected and decoded to restore them into digital data. 5. In this process, the interaction between electric fields and magnetic fields plays an important role. The part related to magnetic fields is significant in the generation and reception of electromagnetic waves. Changes in electromagnetic waves are manifested as changes in electric fields and magnetic fields, and the wave nature of electromagnetic waves arises from these changes. Therefore, principles related to magnetic fields and spins are utilized in some technologies related to electromagnetic waves. For example, magnetic storage devices, e.g., hard disk drives, use magnetic spins to store and retrieve data. In summary, information is converted into digital data and transformed into electromagnetic waves for transmission. The generation and detection of electromagnetic waves involve the interaction between electric fields and magnetic fields, which plays a crucial role in communication via electromagnetic waves and data storage technologies. Semiconductors are materials that play an important role in controlling electric current and processing information. There are various types of semiconductors. Here are the main ones. 1. Silicon semiconductor. Silicon is one of the most widely used semiconductor materials. Silicon chips are used in most computers, smartphones, tablets, and other electronic devices. Silicon is an excellent material that provides stability, reliability, and high performance. 2. Germanium semiconductor. Germanium is a semiconductor material similar to silicon and was used in early computers and electronic devices. However, it is now rarely used due to lower thermal stability and limited range of applications compared to silicon. 3. Compound semiconductors. Compound semiconductors include various compounds in addition to silicon and are used in specific applications. For example, gallium arsenide, GauZ, is used in optical communications and laser diodes. 4. Organic semiconductor. Organic semiconductors are based on organic compounds and are mainly used in flexible electronic devices and organic electronics. Examples of such semiconductors include organic solar cells and organic light-emitting diodes, OLEDs. 5. Semiconductor nanostructures. Semiconductor nanostructures are semiconductor devices fabricated at a very small scale with dimensions on the order of nanometers. These nanostructures play an important role in the fields of nanoelectronics and nanotechnology. 6. Superconductor. Superconductors are materials that exhibit zero electrical resistance at specific temperatures and are used in specialized applications. Superconductors are used in devices for generating magnetic fields and superconducting transmission. These different types of semiconductors are used in various fields such as electronics, communications, solar cells, optics, and nanotechnology. Yes, semiconductors are also commonly classified as p-type and n-type based on their electrical characteristics. P-type and n-type semiconductors have different properties due to their electrical behavior, which is important for semiconductor device manufacturing and electronic circuit design. Here are brief explanations of each type. Semiconductors are also commonly classified as p-type and n-type based on their electrical characteristics. Here are brief explanations of each type. 1. P-type semiconductor. P-type semiconductors have holes as the primary charge carriers. Holes are the absence of electrons and carry a positive charge, acting electrically as positive charges. To create a p-type semiconductor, impurities such as boron are added to the material through a process called doping, creating defects that have positive charges. This results in the generation of holes, and an electrical attraction occurs between electrons and holes. When p-type and n-type semiconductors are combined, a p-n junction is created, which is one of the fundamental components of various semiconductor devices and diodes. 2. N-type semiconductor. N-type semiconductors have electrons as the primary charge carriers. Electrons carry a negative charge and act electrically as negative charges. To create an N-type semiconductor, impurities such as phosphorus are added to the material through doping, introducing additional free electrons. This results in an increased number of electrons, and they act electrically as negative charges. When N-type and P-type semiconductors are combined, a p-n junction is created, which is one of the fundamental components of various semiconductor devices and diodes. The combination of p-type and n-type semiconductors is used to create basic building blocks for semiconductor devices and direct current electron sharing. The p-n junction plays a crucial role in controlling the operation of semiconductor devices and creating electronic switches.